So, with respect to the aqueous reactions chapter, there are three primary types of reactions that are discussed. One of those was the precipitation reaction, which we discussed Monday in the laboratory. The second is an acid-base neutralization reaction, and the third is a redox reaction. We're going to start with acid-base neutralization reactions at this time. So, first of all, when we talk about an acid-base neutralization reaction, it is identifying the reactants. You have an aqueous acid, an aqueous base. One of the products will be the pure liquid water, and the other product will be an ionic salt. A salt, folks, is just a term for an ionic compound. So any salt, I mean, we're used to talking about table salt. The word salt came from the fact that sodium chloride is an ionic compound. It's actually a more generic term than what we're used to talking about. So again, the reactants are an acid that is aqueous, a base that is aqueous. They react to form water as a product and some ionic compound. When we're talking about an acid-base neutralization reaction, we're specifically talking about the Arrhenius definition of an acid, which is a proton donor. Now, we can't have naked protons running around in solution, so those protons react with the water in solution to make the hydronium ion. But what you're going to see is that as chemists, we use the proton and the hydronium formulas interchangeably when we're talking about the chemical reactions. So again, we're talking about a proton donor. It is this proton that goes in, is one of the pieces that makes the water. Now, whoops. Acids can be listed as monoprotic, diprotic, triprotic, or polyprotic. Basically, what we're doing is we're describing how many acidic hydrogens there are. In a monoprotic acid, it means that there's only one single acidic hydrogen. Some monoprotic acids that you may be familiar with include hydrochloric acid. In the case of hydrochloric acid, the acidic hydrogen of the hydrochloric acid will combine with a molecule of pure water to make the hydronium ion and a chloride ion. Another acid that you may be familiar with is the weak acid, acetic acid. Acetic acid is the common component of vinegar. Again, it's a monoprotic acid, so it has a single acidic hydrogen. That acidic hydrogen is donated to the water to make hydronium, and what remains is the acetate ion. So again, a monoprotic acid is simply going to be an acid that has a single acidic proton. Now, acids can also be listed as diprotic, meaning they have two acidic hydrogens, triprotic, meaning they have three acidic hydrogens, or polyprotic, meaning they have more than that, more than three. Diprotic, an example of a diprotic acid is sulfuric acid. Now, an example of a triprotic acid would be phosphoric acid. Those are just common acids that are examples of these types of acids. Now, when we do have a polyprotic acid, the acid is going to dissociate or ionize in sequential steps, meaning that, for example, sulfuric acid, it is going to donate one proton to water to make hydronium and the hydrogen sulfate ion, and then the hydrogen sulfate ion is going to donate a second proton to water to make a second hydronium and the sulfate anion. What we find out is in water, this first reaction occurs to a large extent because sulfuric acid is a strong acid. But this second reaction does not occur to any appreciable amounts in water because HSO4 minus is a weak acid. So what are some common acids? I gave you a chart like this on Monday. Some common acids include hydrochloric acid, hydrobromic, hydroiodic. In other words, it's the three middle halides on the periodic table. Nitric acid, sulfuric acid, and perchloric acid. All of those are strong acids, meaning they're going to dissociate entirely in water to form hydronium and the resulting anion. Some common weak acids that we will encounter frequently include acetic acid, hydrofluoric acid. Something that's not up there is phosphoric acid. Those are all examples of weak acids. Weak acids only partially dissociate in water to form the hydronium ion. Again, like I said on Monday, you have to know, number one, what your strong acids are. And then number two, you need to be able to recognize if something is an acid. And the way we, the common notation to help you recognize that something is an acid is either the acidic proton will be listed first, like it is in all of these compounds, or you're going to see the carboxylic acid functional group, which is COOH. And if you have the COOH group, then the hydrogen attached to the oxygen is the acidic hydrogen. But again, these are your strong acids. If it's not a strong acid and it has one of those notations, assume it is a weak acid. Questions about acids? That's half of the acid-base neutralization reaction. The other half is the base. Again, we use the Arrhenius definition of a base when we're talking about an acid-base neutralization reaction. The Arrhenius definition of a base is that it's a hydroxide donor. Now, the hydroxide can be part of the chemical formula, such as sodium hydroxide, calcium hydroxide, barium hydroxide, potassium hydroxide. It can be part of the chemical formula, or in the case of weak bases, it can be the result of the reaction of the base with water. For example, ammonia is a weak base. When ammonia reacts with water, the water donates a proton to the ammonia to make the ammonium ion, and what's left over is the hydroxide ion. So you have the donation of a hydroxide, just like the Arrhenius definition indicates. Now, so an acid donates a proton, and a base donates a hydroxide. Those combined make water. Hence, the reason it is called an acid-base neutralization reaction is because you are neutralizing the acid and neutralizing the base by making water. Questions? So, common bases. Again, your group 1 hydroxides are common bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide. Other common bases include calcium hydroxide, strontium hydroxide, and barium hydroxide. Those folks are your strong bases. Your weak bases would be other hydroxides and ammonia and compounds that contain amines, which we talked about on Monday. So again, your strong bases are going to fall into group 1 hydroxide, calcium, strontium, or barium hydroxide. In other words, your strong bases follow the solubility rules associated with hydroxides as being soluble or slightly soluble. And then your weak bases typically are identified used because they have some sort of amine functional group. Okay, so again, an acid reacts with a base to form water and a salt. The water is the result of the acidic hydrogen reacting with the hydroxide from the base. The salt is the result of the remaining cation from the base reacting with the anion of the acid. The state of matter of everything. The acid is aqueous. The base is aqueous. The water is a pure liquid. The question is about this salt. What is it? Well, if it's an ionic compound, where do I go to figure out what the state of matter is? I do it for all ionic compounds. Go to your solubility rule. That's where you figure out the state of matter of the ionic compound. Now again, we can develop molecular complete net ionic reactions for acid-base neutralization reactions. For the purpose of this class, in an acid-base neutralization reaction, I'm going to use strictly strong bases, meaning they are going to be aqueous, strong electrolytes, meaning they're going to dissociate entirely in water. Now for the acids. All acids are aqueous, but not all of them are strong electrolytes. So you're going to have to determine whether the acid you're dealing with is a strong acid, hence strong electrolyte, or whether it's a weak acid, hence weak electrolyte. Because as we go from the molecular equation to the complete ionic and net ionic equation, we only break apart the strong electrolytes. So let's actually do a problem. Write the molecular complete ionic and net ionic equation for the reaction between hydrobromic acid and sodium hydroxide. Hydrobromic acid is HBr. Sodium hydroxide means that it has a sodium ion and the hydroxide ion. So our reactants are HBr and sodium hydroxide. The acidic hydrogen from the acid reacts with the hydroxide from the base to make water. The Na plus reacts with the bromide from the acid to make NaBr. In other words, this is a double displacement reaction, just like precipitation reactions are. The only difference is one of the products is water. Now we need to determine the state of matter. As I've said multiple times, acids will be aqueous. I told you I will be working with strong bases. Strong bases will be aqueous. I've mentioned the fact that the water will be a pure liquid. And then you have the ionic compound. And the way you determine the state of matter of the ionic compound is to use the solubility rules. Solubility rule number 1 says if it's got group 1 in it, or ammonium, it's soluble. Therefore, this sodium bromide is aqueous. So, HBr, what type of acid is it? It's a strong acid. And if it's a strong acid, that means it's a strong electrolyte. Sodium hydroxide is a strong base, which means it's a strong electrolyte. What type of compound is water? It's a molecular compound, and therefore it is a non-electrolyte. And then sodium bromide being the an aqueous ionic compound, that means it's soluble ionic. And soluble ionic compounds are what type of electrolyte? They're strong electrolytes. So we will be dissociating the hydrobromic acid, the sodium hydroxide, and the sodium bromide as we move from the molecular equation to the complete ionic. The hydrobromic acid dissociates into hydrogen ion and bromide ion. The ions will have the same state of matter as the parent compound. Sodium hydroxide, being a strong electrolyte, is going to dissociate entirely into its ions of sodium ion and hydroxide ion. The ions will have the same state of matter as the parent compound. That goes to make water. Since water is not a strong electrolyte, water is brought down into the equation. And then you have your sodium bromide, which is a strong electrolyte that dissociates into sodium ion and bromide ion. The ions will have the same state of matter as the parent compound. That is your complete ionic equation. To go from the complete ionic equation to the net ionic equation, you remove the spectator ions. Those are ions that appear the same on the reactant side as they do on the product side. On the reactant side, I have H plus aqueous. Do I have H plus aqueous on the product side? No, so I bring the H plus aqueous down into the net ionic equation. On the reactant side, I have bromine minus aqueous. Do I have bromine minus aqueous on the product side? Yes, so bromide is a spectator ion in this process. On the reactant side, I have Na plus aqueous. Do I have Na plus aqueous on the product side? Yes, so sodium ion is also a spectator in this process. On the reactant side, I have OH minus aqueous. Do I have OH minus aqueous on the product side? No, so I bring it down. And once you've gone through all of your reactants, any product that is still remaining can be brought down into the net ionic equation. One note that I'm going to give you that will make things faster usually on an exam. If I ask for the net ionic equation of a strong acid, strong base reaction, it will always have
H plus OH minus goes to form water as the net ionic equation. As long as it's a strong acid and a strong base, this will be the net ionic equation for the neutralization reaction. It is only true for a strong acid and a strong base neutralization reaction. Let's look at another example. Let's look at the reaction of hydrofluoric acid with rubidium hydroxide. Hydrofluoric acid is HF aqueous. Calcium hydroxide, whoops. Excuse me, rubidium hydroxide has the formula RbOH aqueous. That is going to go to form water. And what will be the other product? It will be rubidium fluoride, which I will give you is aqueous. Because we don't have well, we did have a group 1 rule, so. The reason it's rubidium fluoride is you're going to take the cation of the base and react it with the anion of the acid. This equation is already balanced, so we don't have to balance the reaction, but we do need to determine what we're working with. What is HF? It's an acid, but what kind of acid? I hear strong and weak. One of those is right. It's a weak acid, which means it's a weak electrolyte. Rubidium hydroxide is a strong base, so it is a strong electrolyte. Water, we've already said, is a molecular compound, so it's a non-electrolyte. And rubidium fluoride is a soluble ionic compound because of rule 1, so it's a strong electrolyte. You have to take the time to do that step because since HF is a weak electrolyte, we bring it down into the complete ionic reaction. We bring it down because the only thing we dissociate are strong electrolytes. Now our rubidium hydroxide, we're going to dissociate it into rubidium ion and hydroxide ion. The water is a non-electrolyte, so it is brought down. And we have rubidium fluoride. Rubidium fluoride being a strong electrolyte, we are going to dissociate it into its ions. Now to get to the net ionic equation, we remove the spectator ions. The only spectator ion in this reaction is the rubidium ion. Everything else must come down into the net ionic equation. You will notice that the note I gave you on the previous slide does not fit in this case. Again, the fact that it is H plus OH minus goes to form water for a net ionic equation only works if you're working with a strong acid. Otherwise, you got to figure it out. Questions? Okay.
One type of reaction that's in this chapter that we really don't get too much into, even though you did absorb it to some degree, is a gas evolution reaction. Gas evolution just means that a gas is a result of the reaction. Meaning we're going to observe some bubbles when the reaction occurs. Now, like precipitation reactions, the cation from one reactant combines with the anion from the second reactant. It's just when that occurs, sometimes it produces a gas immediately, and sometimes the gas is the result of an intermediate reaction that goes on. But basically, as reactions, whether they're precipitation reactions or acid-base neutralization reactions or acid reactions with a metal, you can get gas as a product. Now, there are certain types of reactions that we're going to discuss. Types of compounds that undergo gas evolution. One of those is going to be a sulfide. If you react a sulfide with an acid, you're going to produce H2S gas, which is deadly, in enough quantity. I mean, any gas, I guess, is deadly in enough quantity, but H2S is nasty. So again, if you react a sulfide with an acid, you're going to get H2S gas as a result. Carbonates and bicarbonates. If you react carbonates and bicarbonates with an acid, you're going to wind up getting carbon dioxide as a secondary product. An example of this is if you've ever made or seen one of those volcano reactions. You reacted baking soda, which is sodium bicarbonate, with an acid, which happened to be acetic acid. And you got nice bubbles, which was carbon dioxide being generated. You'll notice the first two, you had to react it with an acid. The third one also has to be reacted with an acid. You take sulfites and bisulfites, SO3 and H2SO, or excuse me, SO3 and S2O3s. If you react a sulfite or a bisulfite with an acid, you're going to get sulfur dioxide as one of the gases that's being produced. or one of the products that's being produced. The last one, you take an ammonium salt and react it with a base, specifically a hydroxide base. You're going to make ammonium hydroxide as the intermediate, which is going to wind up making ammonia gas. So, sulfides and acids, you get H2S. Carbonates, bicarbonates, and acid, you get CO2. Sulfites and bisulfites with an acid, you get SO2. Ammonium with a base, you get ammonia. So let's just look at this reaction. Complete the balanced gas evolution equation between hydrobromic acid and nickel 2 sulfide. Okay, hydrobromic acid is HBr aqueous. That is reacted with nickel 2 sulfide, which is Ni2 plus, and sulfide is S2 minus. So therefore, we're talking NiS. Now, what is the state of matter of NiS? Well, it's an ionic compound. Where do I go for ionic compounds? Solubility rules. If you look at the solubility rule, this is going to be a solid. Because I have an acid with a sulfide, I know that one of my products is going to be H2S. And that will be a gas. The other product will be the result of nickel reacting with bromine to make NiBr2. Again, NiBr2 is an ionic compound, so I go to the solubility rules. According to the solubility rules, chlorides, bromides, and iodides are soluble except for lead 2+, silver plus, and mercury 2,2+. Since this is not one of the exceptions, that means that this is aqueous. Finishing to balance this equation, I'll need 2 acids for every 1 nickel sulfide. Questions? Yes. No, just the molecular. Actually, probably just telling me what gas is formed, because there's going to be plenty of other math problems on this next test, which are going to take some time. So if I had to learn one thing, it would be this. I had to learn one thing, it would be that. You're going to have plenty of other stuff to develop the molecular equation, the complete ionic and net ionic equation for. Questions? Okay.
The last type of reaction that is going to be discussed in this chapter is an oxidation reduction reaction, which you actually have to know the information for in order to be able to complete the lab. Oxidation reduction reactions are also known as redox reactions. The red coming from the reduction and the ox coming from the oxidation. Basically, redox reactions involve a transfer of electrons, and we follow those electrons as they move from reactant to product. Redox reactions must always occur in concert with one another, meaning you can't have a reduction reaction unless you also have an oxidation reaction. That's because we can't have just an electron around. We got to have it coming from somebody and going to somebody else. Now, to help remember oxidation and reduction, you can learn oil rig. Oil stands for oxidation is loss of electrons, meaning that the oxidation state will become more positive as we follow the electrons from reactant to product. Rig stands for reduction is gain of electrons, meaning the oxidation state is going to become more negative as we follow the element from the reactant side to the product side. When I'm talking about this, I'm thinking of a number line. And you don't have to go into the negative. All you got to do is become more negative, meaning you have to go, you could go from +4 to +2, and that would be reduction. You could go from 0 to +7, that would be oxidation, or -1 to 0, and that would be oxidation. All you've got to do is move in the direction to be oxidized or reduced. You will notice that in order for us to do oil rig, we've got to follow the oxidation states. If we don't know the oxidation states, we can't figure out who's being oxidized and who's being reduced. There are rules for figuring out the oxidation states. You will need to memorize these rules. If you're one of those that puts a star by things, you will need to memorize these rules. First rule is about a free element. A free element has an oxidation state of 0. There is no exception to that. How are you going to recognize that you're dealing with a free element? It's going to be a compound that consists of only one type of element. That compound is neutral. Again, it's going to be a compound that consists of only one type of element, and that compound is neutral. If you have that, you've got a free element. The next one says that a monoatomic ion is equal to its charge. So in other words, in my reaction, if I have Na+, then the oxidation state is also a +1. If I have O2-, then the oxidation state is a -2. So for a monoatomic ion, meaning that you're looking at compounds that are charged, or I should say elements that are charged. Monoatomic ions are elements that are charged. Their charge and their oxidation state are one and the same. Now, a rule that sometimes you'll find, sometimes you won't find, I find it very useful to think of, is if I'm dealing with cations or elemental anions.
The oxidation state is equal to the charge on those ions. So if I see sulfur as the anion, I automatically know sulfur's a -2 charge. It's also going to be a -2 oxidation state. If I see calcium floating around, calcium's always a +2, so it's going to have a +2 oxidation state. The next three deal with hydrogen, oxygen, and halogens. Hydrogen is always a +1 with one type of exception. And the only type of exception is if the other element is a metal, meaning you have a hydride, meaning hydrogen is acting as an anion. If hydrogen is acting as an anion, then the hydrogen's a -1. But as long as hydrogen is not acting as an anion, it's a +1. Oxygen is a -2. The only exception to that will be a peroxide, and I will let you know if it's a peroxide. If it's a peroxide, then the oxidation state is a -1. Finally, halogens. Halogens are almost always a -1, but there are exceptions to this. The first exception deals with halogen combined with oxygen. In other words, we're talking about perchlorate, chlorate, hyperbromous acid, or excuse me, hyperbromide, stuff like that. If the halogen is paired with an oxygen, the oxygen rule is more important. These are written in order of importance. The oxygen rule is more important. And so the oxygen's a -2, and you'll have to figure out what the halogen is. The other example is if you've got two halogens together, like ClF3. If you have two halogens together, then the small halogen is the -1. You'll have to calculate the other halogen. If it's not listed here, it has to be calculated. The way we calculate this is very similar to the way we determine charge on those metals that could have multiple charges. In other words, we're going to set up an algebraic equation and solve for x. Now, if the compound is charge neutral, we set that algebraic equation equal to 0. But if the compound is charged, like for a polyatomic ion, then the algebraic equation is set equal to the charge on the ion. So let's look at some examples. Cl2. Cl2 is a free element. We know it's a free element because this compound consists of only one type of element and it's neutral. Therefore, the chlorines have a zero charge oxidation state. Na plus. This is a monoatomic ion. Therefore, the oxidation state is the same as its charge, so it would have a +1. Kf. This is an ionic compound. When we deal with ionic compounds, the cation has the same oxidation state as its charge. Well, if that's a +1, since potassium's a +1, that means its oxidation state is a +1. Since fluoride is an anion in this case, again, the oxidation state is equal to the charge, so it's a -1. Let's look at carbon dioxide, though. If you follow the rules, this isn't a
free element. This isn't a monoatomic ion. This isn't an ionic compound. So we don't have hydrogen, but we do have oxygen. Oxygen's a -2 unless it is part of a peroxide, in which case it's a -1. This is not a peroxide, or I would have told you it was a peroxide. Now, to set up the equation, we have one carbon whose oxidation state we don't know. So 1 times X, we have 2 oxygens times a -2, that's a -4, and this compound was neutral, so we set it equal to 0. 1X is equal to 4, so X equals 4. So the oxidation state for the carbon is a +4, and the oxidation state for our oxygen is a -2. Let's deal with sulfate. Sulfate, again, it's not a free element. It's not a monoatomic ion. It is not part of an ionic compound. It does not have hydrogen. So the first rule that applies is the oxygen rule. So it's a -2. There is no rule for sulfur, so we're going to have to calculate it. There's 1 sulfur times X. There's 4 oxygens times a -2, that's a -8. And because this is a polyatomic ion, we're going to set it equal to its charge. 1X equals 6, so X is equal to 6. So our sulfur in this case has a +6 oxidation state, and the oxygen has a -2 oxidation state. In the next one, K2O2. I tell you it's a peroxide. But before we get there, we can go through the rules. There's not a free element here. We're not talking about a monoatomic ion. We are talking about an ionic compound. For ionic compounds, the metals are going to have the same oxidation state as their charge. So that's going to be a +1. And in this particular case, I tell you that the oxygen is part of a peroxide. When oxygen's a part of a peroxide, it is a -1. So the potassium's a +1 and the oxygen's a -1 oxidation state. Questions? I'm just following the rules, step by step by step. Now, folks, here's something that is useful to know. Once you know the oxidation state for the elements in a polyatomic ion, those oxidation states remain constant, no matter where you find that polyatomic ion. So a minute ago, we figured out that sulfur was a +6 and oxygen a -2. Well, over here, the sulfur is going to be a +6 and the oxygen is going to be a -2 in aluminum sulfate. In sodium sulfate, the sulfur is going to be a +6 and the oxygen is going to be a -2. That is going to be true as long as it is sulfate. I didn't have to recalculate it, in other words. Once you calculate a polyatomic ion once, you're done calculating with that polyatomic ion. Questions? So we started this with redox, which involves the transfer of electrons. We're going to use the oxidation states to identify the redox reaction. Basically, if we see the oxidation states change from reactant to product, then it is going to be considered a redox reaction. But if the oxidation states remain constant from reactant side to product side, then we're not dealing with a redox reaction. Again, they have to occur in concert. You can't have one without the other. There's a couple more definitions that you have to know before we can get into the actual problems that are similar to what you're going to see in the lab. We talked about the element oxidized and the element reduced. You use oil rig to figure out the element oxidized and the element reduced. But because they occur in concert, if you've got an element that's being reduced, it's going to be part of the oxidizing reagent or oxidizing reactant. Redox. They go together. Element reduced, oxidizing reactant. That's because an oxidizing reactant causes somebody else to get oxidized. And if it causes somebody else to get oxidized, then it itself has to undergo reduction. For the reducing agent, it's going to contain the element that is oxidized. Again, redox. They go together. So if you can figure out the element oxidized and the element reduced using that number line, then you can figure out the reducing agent and the oxidizing agent. Let's look at an example of how to do this. This one is very similar to what you'll be doing with the copper reaction plus oxygen that you did in the laboratory. But we're going to do lithium plus oxygen, goes to form 2 lithium oxides. In this case, lithium is a free element. We know it's a free element because this compound consists of only one type of element, and this compound is neutral. So it is a free element. Therefore, the lithium has an oxidation state of 0. The oxygen is a free element. We know it's a free element because this compound consists of only one type of element, and that compound is neutral. Therefore, oxygen has an oxidation state of 0. Now, that goes to make lithium oxide. Lithium oxide is an ionic compound. And when we're dealing with ionic compounds, the oxidation state is the same as their charges. So what is lithium's charge? Well, it's group 1, so it's a +1. And what is oxygen's charge? -2. Now, what you will notice is that lithium's oxidation state changed and oxygen's oxidation state changed. Thinking about a number line, again, if it moves in the positive direction, it is being oxidized, and if it moves in the negative direction, it is being reduced. In this case, lithium goes from a 0 to a +1. So lithium is being oxidized. The oxygen goes from a 0 to a -2. So the oxygen is being reduced. Now we do the redox. Therefore, the reducing agent is the reactant. It's always a reactant. It's never the product. It's always the reactant. The reducing agent is lithium. And we do the other redox. And we find that the oxidizing agent had to be O2. Now, one thing I do want to point out, this is one of the few times you can ignore coefficients. You don't have to pay attention to coefficients when you're determining the oxidation states. You just follow those rules. You don't pay attention to the coefficients when you're determining the oxidation states. Let's look at this one in my last 3 minutes. So I am going to go through the oxidation states rather quickly. Following the rules, oxygen's a -2. So therefore, in this particular case, the sulfur had to be a +6. Oxygen's a -2, hydrogen's a +1. Hydrogen's a +1, oxygen's a -2, sulfur's a +6. We know that because sulfate's always the same, and we calculated the sulfate previously. Sulfur did not undergo a change. Oxygens did not undergo a change. Hydrogen did not undergo a change. This is not a redox reaction. Because in order for it to be a redox reaction, somebody has to undergo a change in their oxidation state. In the laboratory, you will be doing redox reactions with single displacement reactions. The easiest way to identify who is being oxidized and who is being reduced from those single displacement reactions is by looking at the net ionic equation. So that will help you in figuring out who's been oxidized and who's been reduced. Any questions? If not, we start thermo on and a lot more math. This next test is math intense, by the way. I will see you on Monday.